Ready? All right. So welcome back to Grad Student Seminar, everyone. Today we have Willie Lim, and his talk is titled, "What is an Orbifold?"
Okay. Welcome everyone. So today I want to talk about orbifolds in general. This is basically like a study of quotient spaces that are fairly nice. I want to start with this result that hopefully should be familiar with everyone, or at least, it rings a bell. So if I start with a manifold, a smooth manifold M, and then there's a group G that acts smoothly on M, and then this action is also free and properly discontinuous, then it turns out that the quotient space of M by G is a smooth manifold. I think there's no harm in trying to recall what these terms really mean. So free over here basically means that if the element G in the group is not identity, then G has no fixed points. So it doesn't fix any point in the manifold M. Yeah, that's what it means. And then properly discontinuous here is saying that basically for any compact subset, so if K as a subset of M is compact, then if we look at the set of elements G such that the image of G and the image of K under G, that's not, well, if it intersects K, right, then, well, the set of elements that does this is finite. And then basically these two conditions ensure that the quotient space of M to Mg, this is a covering. And then whenever this is the case, then basically we know that the smooth structure on B can be pushed forward to the smooth structure of the quotient space M modulo G. Hence, this quotient space M modulo G is in fact a smooth manifold. Okay. So a question that I have in mind is, what happens if I drop the assumption that the action has to be free? What happens if I don't like this? This is a bit too restricted. What happens if it does any, if it does have any fixed points? Okay. So to answer this question, then if we allow some fixed points, then these fixed points are going to be some singularities on the quotient space, right? Hence, it's not really going to be a smooth manifold anymore. But what kind of spaces are these? Are they still fairly nice? What kind of singularities are they? Are they like some wild singularities that you can, I don't know, God knows what. But it turns out that it's not going to be as bad. So I'm going to introduce the main object of the talk, which is orbifolds. Okay. Oh, firstly, I think I can probably introduce some, easy examples first. So quotient spaces that probably include something like, Sn, the n-sphere, and if you identify antipodal points, then you do get RPN. This is a smooth manifold. And then you also have that if, let's say, you have Rn, and then you have some lattice in Rn, under this action, then you get the n-torus. Again, a smooth manifold. If you, let's say, have the complex plane that's punctured at 0, and then modulo this Iz over here is a set of rotations by of angle 90 degrees. Yeah. Then basically I have something like this is the plane, and then this quadrant is gonna get mapped to the other quadrant over here, and so on and so forth. And then I can look at one of the quadrants. This will be the fundamental domain. And then what it does is that, this boundary and that boundary gets identified. And then when that is the case, then I have something like infinite cylinder. Right? it is still a manifold. But then what happens if I do not remove the origin? So the origin here is like the fixed point of the action, right? So in this case, then what I have is something like a cone, because I add a point at one of the ends of the cylinder, right? I have a cone. And then at this cone point over here, this is a singularity. And at this point, clearly it's not manifold, right? So we are going to look at objects like these, basically. And I'm going to introduce a definition. So an orbifold is very much like a manifold. The only difference is that I want this to be locally homeomorphic to Rn, but also modulo some finite group. Okay, that is the only difference. So this is like the key on the definition. If I want to be a bit more rigorous, then I can probably define this in terms of charts. So for example, being an orbifold means that I have some covering, an open cover UIs. And then in each of these open sets UI, it's, there's a homomorphism between this and then some finite, or it doesn't have to be finite, sorry, some open subset VI that is Euclidean. And then I take the action under some finite group acting on VI to itself. Okay. And then over here, I also say it has to satisfy some certain compatibility conditions. Don't bother so much with this. Basically, it's just to ensure that all these, open covering data glues nicely. But yeah, we're not gonna. I'm not gonna satisfy. I'm not gonna say what these are. Really. Anyway, if there's any questions so far, feel free to interrupt me. If not, I'm just gonna keep going.
Yeah, one question.
Yeah, sure.
Are these capital gamma i's, the finite groups, different in every subset?
Different in every subset? Possibly yes.
Okay.
Possibly yes.
Is there more information you can say about any relationship between them?
So if let's say you have some points, no, hold on, let me see. So in the example before, yeah, there's a cone. This is just, I think, C modulo the rotations. Let's say, I said. Then at this cone point, this is the only singularity. And then the corresponding group would be literally just rotations of order 4. But then every other point outside, then the corresponding group is just going to be trivial one because it's locally Euclidean already. Does that make sense? Right.
Yeah. Okay.
Yeah.
Thank you.
So yeah, they can be different, of course. All right. Next. So with this definition in mind, then we see that the result that we have at the very first start, right, can be modified as follows. So again, if I have a group G that acts smoothly on a smooth manifold M, but if we only require this action to be properly discontinuous, it doesn't have to be free, so we can have some fixed points. Yeah. Then the quotient space now is not necessarily manifold, but I know for sure that it's going to be a smooth orbifold. So that's one of the nice things about it. And then I think with this result as well, we can generate lots of examples. So I think the proof of this result is not too difficult as well. So if I start with some point, let's say X, in the original manifold, yeah. And then if I label X tilde to indicate the point under the quotient space. So this is the orbit of X. Then I know that, I know that basically by the assumption that the action is properly discontinuous, the stabilizer, which I'm gonna denote as gamma X, this is a stabilizer. under G of point X, this is going to be finite by the assumption. Okay. And then, so these stabilizers are going to be the finite groups that we are talking about in the definition of the orbifold. How and why? From here on, I can try to pick a neighborhood. Let's say I'm going to call it nx of x that is invariant under the stabilizer. It's not difficult to construct such a neighborhood, but then I want this to be small enough so such that for all group elements G that is not in the stabilizer, so the ones that map X to somewhere else, then the image under this group is must be disjoint from the original neighborhood Nx. And then by doing so, then this neighborhood will project to a neighborhood U x tilde of x tilde in the quotient space. And then I know that this projection, so U of x tilde, this is just homeomorphic to nx modulo the stabilizer, which is finite. So this is basically something like, Rn modulo finite group. That's the idea. Okay. One thing I can say is, so these finite groups at every point, which I call gamma x over here. Well, in this context, it's going to be the stabilizer. But in general, this is what I'm going to call the isotropic group of x. Okay. Or perhaps of x tilde on the quotient space.
A quick question.
Yeah.
What does it mean to be smooth as an orbifold?
That's a good question. I forgot to mention that actually. So in the definition here, I want the finite groups to act smoothly. That's all.
Okay, thanks.
Yeah. And then if you want this to be, let's say, holomorphic, you can just say that it acts holomorphically. And then if you want this to satisfy any other whatever regularity condition, you just have to modify it accordingly. But the concept is similar nonetheless. Okay. All right, moving on.
Willie?
Yeah. What?
Can you say what what does isotropy mean?
I don't know actually, honestly. I never used this word before. That's a good question. Yeah, honestly, I don't know.
It literally means the same in all directions.
In all directions.
Yeah, so like in physics, like we look out in the universe in all directions and everything looks the same. No idea how that relates.
Yeah, I don't know. Thank you for that.
Okay, I'm just trying to understand like why we would call gamma x the isotropy group of x tilde and like what this means.
Yeah, what it means is basically it allows you to model the neighborhood of x tilde as, Rn modulo this, isotropic group. If it's trivial, then this is just going to be, a regular point. If it's not trivial, then it's going to be Rn modulo this group, whatever that is. As to why it's called isotropic group, that's a good question. I don't know.
Okay, this feels a little bit deep. Okay, something to think about.
Yeah. Oh, another comment I should make is that historically, the term orbifold does not come from nowhere. So this is actually quite an interesting story. This comes from Thurston, although before Thurston, there was another person called Satake that uses the term V manifolds. So V manifolds instead of orbifold. This is Satake. Very back in the ancient times. And then Thurston worked with these things in order to prove some geometrization thing of three manifolds. And then he didn't come up with this term. At first, he would like to call this manifolded, or even 4D mani. I guess it's not very creative. But then some of his colleagues and students don't really like it. And then they went through some democratic process. Other people suggested the term origam. And then one of our faculty members at Stony Brook, which is Dennis Sullivan, suggested spatial dollop. This is Dennis. Although in the end, somebody suggested Orbifold, which stands for orbit manifold, I guess. And people seem to like it, and they stick with that. Okay.
Is this anecdote like in a paper somewhere? Like, where did you find this?
This is in Thurston's paper, actually.
Okay.
So everything I'm going to talk about is based on Thurston's paper on, I think, what is it called? Something about geometry and topology of three manifolds, chapter 13. We talked about all these orbifolds, and there was like one big comment that says everything about these terms and the history behind it. So for those of you who are curious, I would recommend you guys to check it out. Okay. Anyway, I'm going to move on. So with this result, again, I can say that I can generate some easy examples. Well, obviously, every manifold is trivially an orbifold, where every point has an isotropic group that is trivial. Okay, so every group, every point is locally homeomorphic to Rn. And then if we look at, let's say, the complex plane modulo rotations of order n, so we're still gonna get a cone, but then with this cone, we have an associated angle as well. And the angle is going to be 2 pi over n, really. What angle really means is basically, you have the complex plane, we have the Euclidean metric on it. We know the notion of distance and angles. And then if we take the quotient, we wrap it around, we get a cone. And then any circle about centered at this cone point, this is the cone point, is going to have angular measure 2 pi over n. That's just what it means to have some angle. And then if we have the dihedral group acting on a complex plane, then so recall that dihedral group, the way it acts on the complex plane is basically by reflections. So let's say n is 3, so we have reflection lines. They're like that. So reflect, reflect, reflect. I can take the final mental group to be one of the sectors over here. So the one I'm coloring. But notice that if, let's say, I color this ray, the one that perhaps represents the x-axis, under reflection, then we're going to get this and we're going to get that accordingly. And then notice that the other ray over here is different. So hence I'm going to color it in green. That and then that and that. So what I'm trying to say is that if I quotient it under the dihedral group, I'm gonna get like a topological closed sector, something like that. Okay, and notice that I don't glue the two boundary edges, so these two are actually different. And then this point over here is what I call the corner reflector of order n. It's basically like a corner of two reflection lines. So these are like the green and the red one are called mirror lines. This is a mirror, this is a mirror. I mean, topologically, this is just, just a boundary, one-dimensional boundary, really. And then the other example over here that I have is if I have the d-dimensional torus, and then the group acting on it is the group of permutations of the set of the elements. Yeah. If d is equals to 2, then you can, this is just a little basic exercise in geometry topology that you should convince yourself that this object, when d is to 2, is just a Mobius strip. So you have this, torus. We have this usual identification. But then under the group action, we have a symmetry. No, we have a reflection line over here. We can swap x and y accordingly. And this acts as a reflection. And then under this reflection, basically this edge is the same as that edge. So it's the same as this edge. And then if you look at, one of the triangles, you, can do a bit of cut and paste, you get a Mobius strip. And then the boundary of the Mobius strip is going to be this, red reflection line, actually. Hence why I call it mirror boundary. Okay. Also, historically, so when D is, let's say, equal to something, this also has an interpretation in music theory. So in atonal music theory, every note can be represented as, I think, like a point on the circle. And then if you, let's say, have 3 notes played together, so like a triad, then we have, basically 3 points on 3 circles, or hence, T3. But then for triads, it doesn't matter which order you play it. Hence, this space is basically what can appear in the space of triads in the music theory, for example. Okay. Moving on. One of the other examples that I have is this one. So if I have the upper half plane, modulo, this is what we call the modular group. This is the group of Mobius transformations where the coefficients A, B, C, D are in SL2Z. So in other words, the coefficients are integers and then they are of determinant 1. I can say that the generators of this group is -1/z. And this acts like a rotation about I of order 2, so by 180 degrees. It's not really a rotation, it's more like a hyperbolic rotation of the upper half plane. So this is I over here. And then it basically maps everything outside the semicircle passing through this, anything above it to rotate it to below. So up and down here. So if you look at this gray region over here, then this gray region is going to get mapped to this triangular bit. Okay. And then another generator that I can point out as well is z+1. This is just literally just translation by 1. So this gray region gets mapped here by z+1, and then it gets mapped here, and then so on and so forth, something like that. Okay. And then another one, this is not really a generator. I mean, this is the composition of these two guys, which is -1 over z+1. This, in fact, will be a rotation of order 3. About what point? About this point, actually. So this gray region will get mapped to here. No, my bad, not there. To here. And then it will get rotated again to here, and then come back. Okay. And then what can I say about the fundamental domain is the following. So if I draw it again, over here, then I can identify the edges on the left and right by simply the translation. And then by the rotation -1/z, I can identify part of the semicircle, let's say this one, with that. And then convince yourself that in the end, this space, you glue along the boundary lines accordingly, you're gonna get something like a disk, but with 2 cone points, something like that. And then it has 2 cone points. And the cone points over here are associated to this point, I. This is a fixed point of the rotation of order 2 by -1/z. And then the other one is this guy. So this is of order 2, this one is order 3. This one is by the -1 over z plus 1, so 2, something like that. Okay. All right, moving on.
Sorry, I have a quick question about that
Yeah.
example.
Yeah,
So
sure.
the cone points now are cone points where we're visualizing the quotient as embedded in, I don't know, C2 or something like this, right? I mean, in
What
what
do you mean?
sense? I guess my question is, doesn't the topology near the cone point depend on how we're embedding the space?
No. I mean, topology is basically just dependent on, how you glue along these ones, right? I mean, under this gluing, you're just gonna get this. Topologically, it's just a disk, right?
I guess my question is, when we do this gluing and we have one point here which has a isotropic group of order 3, right, and another one that has of order 2.
Yeah.
How are these groups acting when we view? So I understand how they're acting on the upper half plane, but after we perform the gluing, then this is an object which doesn't live in the upper half plane anymore.
No, it does not. Yeah.
So how are they acting now?
How are they acting now?
Because
the group just acts on the upper half plane, doesn't act on the quotient space anymore, does it?
Right.
Yeah.
So okay, so the orbifold. I see. Okay, I see. Okay,
Yeah.
thanks.
There's a comment by Muhammad. This is a very good one, actually. This example is a space of complex structures on a torus. You are very, very much correct. Yeah. Or I think some people prefer to call this the moduli space or Teichmuller space or whatever other terms you fancy. Anyway, moving on. There's a reduction statement over here that basically states that the isotropic groups can be seen as just finite subgroups of the orthogonal group ON. So this will help us, reduce our analysis of what kind of groups actually appear locally. Okay, so this statement requires a bit of a Riemannian geometry. So it kind of goes along like this in the proof. So if I pick some points, say X, and then we have some, small neighborhood. So suppose this neighborhood has some local model of some, X, and O is, something like V modulo G, where V is some Euclidean subspace of Rn, and then G is some, some whatever group acting on V, okay? And then I have some Riemannian metric that I can, just, pick to be, you can pick this to be anything, really. So let, G tilde be a Riemannian metric on V. I mean, you can pick this to be just the Euclidean metric. It doesn't matter. And then what I can do is that I want to pass this metric to the quotient. And one way to do so is basically take the average. So the average, I'm going to call this G hat. And then this is just this guy, and then I'll take a sum over all the possible pullbacks of this metric. Okay, that's what it means by the average, I think. But yeah, what's so good about this is that this is now G invariant. And therefore, it induces a metric, I'm going to call it G, on the local quotient space. Yeah. And then I can restrict V G not tilde anymore. This one is the average one, to the, let's say, epsilon neighborhood. I'm gonna call this V hat of X. And then, well, perhaps it's not really X, it's the, because X is in the orbifold. So technically I'm gonna call this, let's say, X hat, whatever, that lies in V, okay? That corresponds to the point X. And then in this epsilon neighborhood, that I know that G acts isometrically on this V hat with respect to this new average, because I know that, you know, this new metric is G invariant, so it has to act isometrically on this restriction. And then by this thing called the exponential map in Riemann geometry, if you don't know what this finest one, it's not a big deal. We have some diffeomorphism from this V hat modulo G to basically the ball of a radius 3, this lies in Rn, modulo some group. I'm gonna call this oh my bad, where did it go? Gamma X, where gamma X now must be a subgroup of On. The reason being is that now G acts isometrically with respect to this metric. So there's an obvious identification of this G with some subgroup of the orthogonal group. That's, you know, just a rough idea, really. Okay. And the good thing about this is that we know some finite subgroups of On, and in particular in low dimensions in N, let's say 1 or 2 or something, we know all the finite subgroups of On. So, for example, in dimension 1, On, the subgroups of On are literally just the identity, the trivial one, or, you know, plus minus identity. Okay. In dimension 2, this is something that I just found out a few weeks ago, actually. This is theorem by Da Vinci. The only possible finite subgroups of On, of O2, is sort of either the trivial one or the dihedral group, or cyclic rotations of order N. Okay. So for dimension 1, this is the only non-trivial one. And then the way it acts is that if I have a real line and then the origin, so this is like a reflection or perhaps rotation by the origin. And then if we take the quotient, this is going to be topologically like an infinite ray, like 0 to infinity, something like that. Okay. I think more importantly, the only possible singularity that appears over here is really like, you know, like a mirror point, which is the origin over here. And topologically, this is literally just a manifold with boundary, where this boundary acts as a mirror point with respect to this orbifold structure. And then when N is equals to 2, okay, the only non-trivial cases is either the dihedral group or Cn. Oh, my bad. Why does it keep doing that? But yeah, Cn over here, this again generates the cone, right? So one possible singularity is the cone point. And then the dihedral group, again, this is going to create a wedge with 2 mirror lines. And this is what I call corner reflector of order N. And then notice that topologically, the only one that has boundary is the one on the left, is the one that is generated by the dihedral group, okay? And then the boundary over here is this corner reflector point, and then the 2 mirror lines, mirror and a mirror. Meanwhile, the cone point over here, topologically, this is still, you know, Euclidean somewhat. Yeah, not smoothly, but topologically, okay? So this is not a boundary point. Nonetheless, at least for up to dimension 2, we see that every orbifold is homeomorphic to a manifold, a smooth manifold.
Willie, can I ask a question?
With boundary, possibly. Yes.
Why are you calling the boundaries mirrors again? I don't remember.
Because the dihedral group is generated by reflections along these mirror lines. So I call it mirror because it's acting like reflection along this line, the group at least.
Oh, so when the group acts on this, okay,
yeah,
I see what you mean. Yes, okay.
Acts on the plane at least. Yeah. Okay.
Can I ask a question going backwards a bit?
Sure.
So a priori, the finite groups could they didn't have to be an ON. I assume they're still acting on a sphere, so they would be in the diffeomorphism group of Sn or Sn
for
minus
which one?
What do you mean for which one?
Is this like a general question for like any
general
orbital?
question? Like you have discrete groups gamma, which they have at least one fixed point, right?
Doesn't have to be, but okay. Yeah.
Okay. But okay. Well, I was just wondering if your proof was basically proving that the diffeomorphism group of Sn or Sn minus 1, I guess deformation retracts onto On. Because basically
I'm not
you
sure
have
where
like
the Sn comes from. So this is just the local model of at every point. I mean, by definition, orbifold is locally homeomorphic to Rn modulo some finite group. But then a priori, we don't know whether this finite group is, can be taken to be a subgroup of ON. It can be anything else, perhaps, yeah. But we can reduce the statement by saying that, in fact, we can just take this to be a subgroup of ON. Is that clear, perhaps?
Yeah.
Okay. So at least in 2 dimensions, we see that the only 2 possible singularities are either the cone points or corner reflectors. And then notice that corner reflectors always come with, like a boundary. Okay, so the ones without boundary is always the cone points. And then I want to try to attempt doing a bit of a classification statement for low dimensions. So what are the possible, orbifolds out there? What are the associated geometries corresponding to these orbifolds? For dimension 1, I don't think it's difficult to see that, because this is homeomorphic to a manifold no matter what, with boundary possibly, then this is just going to be R or S1, or so 1 with boundary, something like that, or even, just 0, 1. So from 0 to infinity, the 0 is going to be a mirror point. And then 0, 1, from 0 to 1, then the 0 and the 1 are going to be 2 mirror points. Okay. And these are the only 4 possible ones. But what about 2 dimensions? With that, we can try to use a bit of a more advanced machinery.
Wait, sorry, I have a quick question.
Yeah.
So we're classifying up to topological, classifying up to homeomorphism.
Not homeomorphism.
So how are we classifying?
Up to, I haven't really defined functions on orbifolds.
Yeah, because I'm not sure what a map of orbifolds is.
I would say smooth diffeomorphisms. It should be clear in the next slide.
Okay. Okay.
Hopefully. Yeah. Okay. So I want to introduce a bit of extra machinery. This is covering space theory for orbifolds. So the definition is pretty much the same as manifolds or even topological spaces in general. The only difference is that locally, it acts not as a local homeomorphism, but rather as a quotient map between 2 quotients of Rn by some finite groups. So the idea is that, if I have, let's say, the example that I have earlier, the one with 2 cone points, I'm going to call this P. And then if let's say I have some other orbifold over here, or if suppose I look at the cone points on here, I'm going to call it Y, and then I look at the pre-images, and then I look at the corresponding neighborhood. And then at each of these neighborhoods, so this restricted to here, the action of F is not a homeomorphism onto this neighborhood, so UI to V. It's not going to be, not necessarily a homeomorphism. It can be allowed to be just a quotient map between two quotients of Rn by finite groups. What do they actually mean? So I think one easy example I can think of is something like, perhaps R2, so the plane, and then modulo, let's say Cn. Cn here is a cyclic group of order n, right? So this is a cone with angle 2 pi over n. I can wrap this around, k times, and I have, let's say, Cnk. So initially I have some cone of angle 2 pi over n, and then I wrap it round k times. So this is a k to 1 covering map, in fact, into a, well, smaller cone because now the angle is divided by k. Okay. This is not a covering map topologically. This is a branch covering map because it has a fixed point at the origin, at the cone point. Yeah. But we call this an orbifold covering map. Okay. So whenever we have covering maps, we also have universal covering maps. So among all the possible covering maps you can think of, there is the universal one that satisfies universal property. So, the math behind this is pretty much the same. You can try to prove that it does exist by inverse limits. I'm not going to do it for you. It's complicated. But anyway, convince yourself that it does exist. Okay. And then whenever the universal covering map or universal covering space is just a manifold, so there's no singularities or whatsoever, we call it good. So always good whenever we have we can express this as some manifold quotient of this by some properly discontinuous group, basically. And then if it's not good, we call it evil. That's all. Okay. In fact, by introducing this definition, the evil ones do exist. Evil always exists. And lastly, I also want to point out that we can try to define fundamental group as well. So the orbifold fundamental group, I do not wish to define in terms of paths or loops or homotopy or whatsoever. I just define it simply by the direct transformations from the universal covering to this orbifold. Okay. So I think the easy one would be, the cones again. So the infinite cone, let's say R2 modulo Cn. This has the fundamental group of this guy is literally just Cn. It's a finite group of order.
Sorry, Willie.
Yeah.
Are good and evil the official definitions?
I think Thurston uses this, yeah.
Okay.
You just call it good. No other advanced terminology. Yeah. Okay. Other questions? If not, I'm going to move on then. All right. I think I can finish this on time. Good. So there's also this notion of Euler characteristic. So we know the topological Euler characteristic of some, topological space or CW complex in general. Yeah. And this can be defined when it's compact. So if we have a two-dimensional, so now I'm restricting myself to just, two-dimensional compact orbifolds. And then I endow this with some, finite CW complex structure. I attach, some cells, some vertices, edges, and whatsoever. But the way I do it is such that every singular point, so every cone point, every cone reflector point, and every mirror edges is a cell in this CW complex. Yeah, and I call the Euler characteristic as an orbifold of O, to be the following formula, basically. Notice that without the denominator, if I just look at this guy and that guy, right? This is just the usual Euler characteristic, the usual one for a arbitrary CW complex. Now, what is this denominator? So this gamma C is the isotropic group of the cell C. So if, let's say, C is a vertex, which is also a quant point of order n, then, you know, this isotropic group is a Cn, the cycle group of order n. And then, yeah, this is just, you know, the order, basically, of this isotropic group. So if the cell is regular, right, it's not a singularity, then this is going to be 1. Yeah. But if this is a singularity, then, you know, it's going to be 1 over the order. Okay. There's a benefit in defining the Euler characteristic in this way. Okay. The benefit is that we have this formula, a very, very nice formula, so succinct, very, very, it just looks neat. And it corresponds to the usual Riemann-Horowitz formula in the theory of covering spaces as well, which says that basically if we have a covering map of degree D, then the Euler characteristic of the covering space O is just D times the Euler characteristic of P. Okay. And then the proof of this guy as well is not difficult too. So if I, you know, have if this is P, right, maybe this is a point, and then I look at the pre-images of these this point. So 1, 2, 3, 4, and so on and so forth. And then I basically, well, if I label this as maybe x1, x2, x3, and then this is y. Okay. So locally over here, we have isotropic groups. I'm going to call it gamma xi. So locally, we have this, you know, mapping Rn modulo gamma xi, and then mapping to Rn modulo gamma y, which is the isotropic group of y. Okay. And then the degree of this guy, so I don't have space over here. So degree, the local degree at least, at each xi is literally just the ratios of the order of the isotropic groups. So there's a gamma I, no gamma y divided by the order of gamma xi. And then combining all these across all the pre-images, I know for sure that the sum of the local degrees, which is the sum of this guy divided by gamma xi, this is just going to be D, all right? So I'm just summing all the local degrees to get that, to get D in total. And then all I do is that, well, I can try to rearrange this, and I get the sum of 1 divided by gamma xi, and then D times 1 over the order of the isotropic group at y. Okay, and you know, this basically very much resembles the formula, the Riemann-Horowitz formula, because if I look at every cell, then I have this formula, no matter what. So if I combine all the information across all the cells in the CW complex, then gluing them together, I get this, you know, formula, the Riemann-Horowitz formula, basically. Okay.
Sorry, could I ask a question?
Yeah.
I think I missed this, but for the orbifold covering maps, are the covering spaces also orbifolds?
Yeah, possibly, yeah. Yeah.
Like, is it necessarily an orbifold? Like in your Riemann-Horowitz formula, is it interpreted as the orbifold Euler characteristic on
Yes.
both sides?
Yeah, yeah. I mean, if O, let's say, it's just a manifold, then this coincides with the usual Euler characteristic anyway.
Okay.
Because
yeah, I just missed
isotropic groups
the
are going to
part
be
of the
trivial.
definition.
Yeah. So
Okay,
yeah,
thank you.
and then what else do I have? So if I want to classify 2D orbifolds that are compact, I also need to take care of the presence of the boundary as well. But this can be taken care of easily, like as usual. The way we do it is by, so if the orbifold O has topological boundary, I can just consider the double. The double basically is constructed by taking two copies of itself, and then I glue along the boundary line. Yeah. And then I think one example that I have over here is that if I have this orbifold O, this is topologically a disk, but then I have three boundary mirror lines, and then there are 3 points over here that are singular. These are the corner reflector points of order 2, 3, and 5. Okay. Now, if I consider another copy of itself, and then I glue along these two, along, there's a blue with blue, and then red with red, and then green with green, correspondingly, then the two triangles meet and become like a topological sphere like this. But I notice that now these corner reflector points, corner reflector, now become cone points. Under, well, this double is going to have cone points over here instead of corner reflector points. Okay. And then basically we can reduce to the case where the compact orbifolds that we have do not have boundary, because whenever it does have boundary, then we can just consider double. We take this, double covering instead, which is, which is still compact but has no boundary. Okay. And then the very last thing that I would like to say is just the conclusion of this, which is if I have an orbifold O, two-dimensional one that's compact without any boundary, then it has to be one of these. And note that in the table over here, I classify it based on the different geometries. So I call, when the only characteristic is negative, this is what I call hyperbolic. When this is equal to 0, then this is, you can call it flat or parabolic. And then if it's greater than 0, typically this is what we call elliptic. But there will be a bit of a problem because the evil ones do exist. If we only talk about manifolds, no orbifolds, so no cone points or whatsoever, then there are plenty of the hyperbolic ones, but then we can classify the parabolic and the elliptic ones fairly easily. This is just S2 and then RP2. And then the parabolic ones are, they are compact at least, is the 2 torus and then also the Klein bottle. Okay. And then remember the statement earlier that basically every compact orbifold is homeomorphic, so it's topologically equivalent to a manifold. Yeah, and whenever there's no boundary, then it's going to be either of these four really, plus the hyperbolic ones, which are plenty of them, infinitely many of them in fact. And then one thing I would like to note is perhaps the evil one. The evil one does exist. Evil exists. And then there's only 2 types, fortunately. So here, the 2 types is, the notation that I use is these MIs are the orders of the singularities of the cone. So whenever there's more than 2 cone points, it's going to be all right, it's going to be good. But if there's only 2 cone points or only 1, then there might be a bit of a trouble. So the first one I can clarify is perhaps the one where there's only 1 cone point. So we look at the sphere, but with 1 cone point, something like that. This is what I call the teardrop. Now, if you notice the Euler characteristic of this guy, so Euler characteristic of O, you can try to compute this. It's just going to be 1 plus 1 over m. All right. Now, notice that this Euler characteristic of S2 divided by this is not an integer. So the conclusion is that by Riemann-Hurwitz formula, it cannot be covered by S2. So in other words, in fact, this teardrop is actually simply connected as an orbifold, and it cannot be covered by S2. Okay, and then the other one, the other evil one, is one where we have two conpoints. So this is M1 of order M2 over here. This is what Thurston called spindle. If we compute the Euler characteristic of this guy, it's going to be 1 divided by 1 M1 and then 1 divided by M2. And then for the same reason, the ratio of Euler characteristic of S2, which is 2, so 2 divided by this guy, is an integer if and only if M1 coincides with M2. Yeah. So whenever the order of the two conpoints are different, then it's actually going to be it's not going to be covered by S2, right? By the Riemann-Hurwitz formula. And then for the other ones, I'm not going to explain to you in detail why or how I get these numbers. I think you can use like the same kind of argument using Riemann-Hurwitz formula, claim that, oh, the ratio between, let's say, Euler characteristic of S2 divided by this guy is going to be an integer, and therefore it can be covered somewhat, somehow. You can also prove this constructively, like, you know, can I construct the universe cover by hand? Okay. And then for the ones with 3 numbers, at least, this one and that one, and that one and that one and that one, these can be constructed by, if you have like a triangular lattice on the sphere or on the plane, and you look at the space or the symmetries of this triangulation. So, you know, that means the reflections along the edges of the triangles. Yeah. If you look at the subgroup of the orientation preserving actions of the symmetry, so in other words, the rotations along the vertices of the triangles, then you're gonna get precisely these guys. So that's what's happening. And then for the other ones, the story is a little more complicated, but I think I'm running out of time here. So that's all I can say. Okay. Well, I hope it's interesting. Are there any questions?
Yeah, a quick question. So is somehow the idea supposed to be for an orbifold covering map that the preimage of any point, the stabilizer there should be is not quite as bad as the, not the stabilizer, the isotropic group is not quite as bad as the one in the image.
For the covering map.
Right, because you want
yeah.
Okay.
That's the idea. Yeah.
So as you pass the coverings, the singularities should somehow get better.
Yes, okay. That is the idea. So if you look at the universal covering, this should be the least bad. Yeah, I think that's a word. Okay, so you should expect the singularities to be reduced multiple times, and then you're gonna get this really. And then, so the only possible universal covers over here is literally just, you know, S2, R2. If you consider R2 to be geometrically different, we also consider the hyperbolic space, the upper half plane, let's say, plus also the evil ones. So the evil ones here are the teardrops and also the spindle when M1 and M2, the orders of the spindle, are coprimes. Yeah. So those are the only possible universal covers for orbifolds, at least. Any other questions?
If if M1 and M2 were both 3,
Yeah.
why would the quotient be an integer in this case?
It's so if 3, you're gonna get 2 over 3, isn't it? Yeah.
Yeah.
But then by the Riemann-Horowitz formula. Okay,
You are
so
dividing by
this
x0.
fraction,
Yeah, you get.
it's gonna be 3 then, isn't it? Because you have 2 divided by 2/3. So you're gonna get
Oh,
2.
so it's okay.
Yeah. And in
That's
fact, when
because
it's 3, I
the
can
Euler
also like,
characteristic of S2 is 2.
yeah,
Okay.
exactly. So you want to make sure that the Euler characteristic is like, either 0. When it's 0, you're just gonna get the elliptic one. No, the parabolic ones. But if it's elliptic, you want to make sure that it's 2 over something. It has to be over the form 2 over something. And this something has to be an integer, no matter what. And then I think I can probably also say that if you have the sphere, and then you have this, and then you make like a triangulation that goes like that. I'm not very good at drawing. That, and then also that. I can do like a rotation about here. I can also do like a rotation about each of these points as well. But it's not difficult to make. No, we don't need this line actually. Never mind. Yeah, I think just a rotation about like 2 antipodal ones. That's gonna create a spindle. That is good. So 3, 3.
Okay, that makes sense.
Any other questions?
A quick question. Does
Yeah.
the spindle cover the teardrop?
This one? It does not.
Okay.
It does not. So the teardrop over here. Let me think. So the teardrop here, yeah. If let's say this has singularity m. I think one thing I can say is that without the argument in terms of Riemann-Horowitz formula or Euler characteristic whatsoever, if I remove the con point, this is just a disk. It's already simply connected. So one thing I can say to you is that, if I remove this, it's already simply connected, right? And what happens if I just attach, this extra point? Will it actually do anything? Is it actually possible to create another, universe cover out of this, really? And the answer is actually no, somehow. I think this is the argument that is used by Thurston, saying that, the teardrop is obviously not, is obviously evil. We cannot, have some other covering of the teardrop simply because of this reason somehow.
Thank you.
Yeah. Any other questions?
For that talk, that was really cool. So,
That was really good.
Thank you, guys.
Thank you.
Yeah, great talk, Willie. Thanks.
yeah,
Thank you.
I guess that concludes our meeting for today, but hope to see you all next week and have a good weekend, everyone.
Bye-bye.